Okay, time for another video presentation. Today we're going to follow up with the topic of momentum and talk about conservation of momentum. So that's today's topic, conservation of momentum. So the idea of conservation of momentum, and there's the physics definition on the screen, but really the idea is that something's going to happen. Something's going to happen, and in our case it's going to be something between two objects. We're going to limit it to two objects. And the momentum of the two objects beforehand is going to be equal to the momentum of the two objects afterwards. In real life, it could work with any number of objects. It doesn't have to be two objects. It could be, well, any number of objects, like I said. But in our case, we'll talk about two objects and that there's going to be the conservation of momentum. So the momentum before something happens is going to be equal to what happens afterwards. So for our examples, it's basically going to be collisions that we look at. So conservation of momentum in collisions. Okay, the recoil of a gun is a good example of this one. And if you've ever fired a gun, you know that there is a little bit of a kickback or a recoil that they talk about. Well, what happens there is you fire the gun, and the bullet goes one way, but there's a backwards movement of the gun itself. So the bullet has momentum going this way, there's a small bullet going at a very fast speed, and then there's the larger rifle going at a slower speed in the other direction. So here's a video that shows that in slow motion. So let's take a look at that. And here you can see somebody's at a shooting range, and you can see the kickback there once they pull the trigger. Yeah, so you can't see the bullet flying off, but you can see the kickback. And that is the idea of that. All right, very interesting stuff there. So if you're ever in the situation of firing a gun, do not hold it in front of your face. That's going to be painful. It could come back and hit you. All right, so gun recoil is an example. Another example, a classic one, is what they call the Newton's cradle. So the idea of the Newton's cradle is that, well, you've seen these things with the Newton's cradle. It's really hard to walk by them without pulling one into the thing and letting them bounce here. But there you can see you pull one ball back, and the one ball is going to fire in the opposite direction. It's going to go in the opposite direction. So how about if two balls collide? What's going to happen? Can you make a prediction? What do you think is going to happen? Can you picture it? Well, here we go. Two balls flying out the other side, back and forth moment. Whoa, well there's only 5 of them. What happens if we pull 3 balls back? How are we going to conserve momentum there? Well, let's see what we got going on here. Okay, you must trust physics. All right, so pull back 3, and what's going to happen? There's only 2 balls. How is momentum going to be conserved? Well, boom, 3 balls are going to go out on the other end. So there's going to be a transfer of the momentum. So that's the idea of that one. And with 4 balls, you can predict it. It'll be a similar kind of deal. 4 balls going the other way. And this is the Newton's cradle. All right, well, how about this one? 1 ball on each side. How's momentum going to be conserved in this example? Well, there you go. 1 ball bounces back from each side. And oh, how about this one? This is a little bit tricky. 1 ball on one side, 2 on the other side. How is momentum going to be conserved here? Well, let's see. It's just a switch of momentum, 2 and 1. Stays the same no matter what. That's the idea of this, conservation of momentum. So a couple more examples for you. And I think this will be the last one that I'll show you, and then we'll move on. All right. So that's the idea of the Newton's cradle, pretty famous business over there. Yeah, you see those on a lot of people's desks. Very hard to walk by those without giving it a shot. All right, so that's the idea of Newton's cradle and the conservation of momentum. Newton's cradle. Here's a cannonball, same idea as the gun recoil. If you have a cannon on wheels, it's going to go backwards while the cannonball goes forwards, and there's a picture of the Newton's cradle for you. Okay, so a little bit of definitions here. Inelastic collision. This is going to be one where the two objects stick together. A classic example for physics, and in real life too, is if there's a collision with cars and the bumpers lock together. And whether the bumpers lock together or not, they do use the idea of conservation of momentum in investigating traffic scenes. And we'll do a little bit of that in class too. Okay, let's get the lights going back on here. All right, that's not too bad. All right, so let's see, conservation of momentum. The idea again is, as I've said before, that the momentum beforehand is going to be equal to the momentum afterwards. And we will limit our calculations to collisions of all kinds of objects. All right, so momentum before is equal to momentum afterwards. That's the overriding theme here of this whole topic. So here's an example, and just like every other problem that we've done, we're going to identify the information first. Now here it's a little tricky sorting out all these words, and it becomes a little bit of bookkeeping. A lot of 5s and 10s to float around. But I've got a 5 kilogram object, and it's moving at a certain speed, and then I've got a 10 kilogram object. So we know that m is the symbol for mass, and kilograms are masses, so this is a mass of 5 kilograms and a mass of 10 kilograms. I'm going to call this one mass number 1 and this one mass number 2, and that's how I'm going to do my bookkeeping on this to identify my information. So when I did that, this is what I came up with for the masses, their initial speeds, their final speeds, and you can see here all the information is identified. And after identifying the information, it's a matter of plugging it into the equation. So there's the momentum before and the momentum afterwards. And here, since momentum is mass multiplied by speed, the momentum before is going to be dealing with the initial speed. And I've done that for both of the masses. And the momentum afterwards is going to be the mass multiplied by the final speed. And hopefully that makes some sense. When I plug in the numbers that I identified from the beginning, this is what I get. And a little bit of reduction in the calculations. Of course, 0 multiplied by anything is 0. So these two areas cancel out. And then I'm going to undo this last step here with division. And I'm going to come up with my answer that is 5 meters per second. So hopefully you understood how I did that. And you know, and if not, I know all this physics can be complicated. Bring your questions back to class. We can talk about it there. Okay, remember inelastic collisions are collisions where things are sticking together, and I mentioned car accidents are one way of one time that happens. So here's an example of that. Once again, I've got 2 different masses. We're always going to be 2 masses in our conservation of momentum problems. And here's a 1,000 kilogram car. I'll call that mass number 1. And it strikes another 1,000 kilogram car. I'll call that mass number 2. And here we got the mass number 1 is moving. The other car is just sitting there. And then they stick together after the collision. So as always, I am going to identify the information, remembering that since the cars are sticking together after the collision, I might as well talk about the mass as being the combination of the 2 masses. I'll show you what I mean by that. Okay, here's my identification of the information over here. So I've got my 2 different masses and their speeds, and it's the final speed that I'm looking for. Here I'm not talking about 2 different final speeds, because there is only one final speed since they stick together after the collision. So my setup here again before I get started is just going to be a little bit different on the right hand side of the equation where the 2 masses are going to be added together afterwards. Since they stick together, I might as well add their mass together. And when I do that, I'm just plugging in the numbers here, I'm ready to go. So here's my 2 masses added together, which is going to look like this. Remember, 0 multiplied by anything is 0. So here's 20,000. That's my 20 multiplied by 1,000. And here's my 2,000 multiplied by V final. So when I do my division, I'm going to get my answer for V final, and that turns out to be 10 meters per second. Hopefully this made sense to you. Again, I understand that it can be confusing, so if you have any questions, bring them back to class, and we'll talk about them there. Look forward to seeing you there. Thanks for watching.